I want to introduce what are called implicit schemes. Now, I'll point out something important about implicit schemes in a minute, but for right now, let's just go back to our original problem, which was to say, look, when I had this thing here, un minus 1. So let's go back to where we started, which was du dt equals this here. And then when we said, basically, it's like, hey, you know what we could do is we can apply that Floyd-Euler here, simplest thing possible, which is to say, how about we do the following? U of m plus 1 n minus u of m n all over delta t. I'm going to approximate my derivative that way, right? So we said that. Everybody go with that? Now, here's something to observe. Then we just simply said, hey, let's now evaluate this right-hand side. And I didn't really make a big deal about this, but I made a huge assumption here. I said, we're going to evaluate this right-hand side. We have to pick a time when to evaluate it, right? We've decided how to evaluate this left side at what times, at time m and time m plus 1. And on the right, we just said, well, since I have time m, why don't we just evaluate it then? But you could just as easily say, I'll evaluate it not at time m, but at time m plus 1. Right? I'm working in this interval. I could do that. Now, here's what's kind of silly about it in a way, which is to say, my solution in the future is what it is right now, plus a little bit of the future. Well, I don't know what the future is, right? I'm supposed to determine that. So this is why it's called an implicit scheme. You have it all wrapped up in there. Now, in this case here, you can actually rewrite things by collecting your future points together. And what you end up with is the following. A, vector u at m plus 1 is equal to um, where the matrix A looks like the following. 1/2, 2's on the diagonal, negative lambda on this, and lambda here. So notice what I've got to do. If I want to take one step forward into the future, I've got to solve for the future point, un plus 1, right? This is a linear system of equations. So I say, I want my future point. Well, to get your future, you've got to solve ax equal to b. Right? So in the other schemes, by the way, generically to solve ax equal to b costs you order n cubed. Once you do your factorization, maybe you get down to order n squared. But the point is, in the other schemes, you just do matrix multiplies. Here, you've got to solve a linear system of equations that could actually be quite large, first of all. So why would you do that? Right? You can ask that question, that seems stupid. It's a lot of extra work. And here is why you would do this. This scheme is stable for all lambda. No matter what you pick your CFL condition to be, this thing is a stable scheme. That's different from saying it's accurate. Right? You get to pick accuracy by choosing delta t, delta x, but it doesn't matter. There's no CFL condition to violate. This is why people like implicit schemes. People like implicit schemes because there's like this amazing thing that it does for you if you consider it from the perspective of the stability of a scheme. But it costs you. Right? There's a price tag for everything. The price tag here is pretty high. And by the way, this is a linear system. And notice with a linear system, I could solve it. Suppose this is a nonlinear PDE. You're not solving it. Okay? Right? Because then you got to, well, you could solve it, right? You'd have to do what we did in homework 2, which is go solve a nonlinear set of equations. How fun is that? Nobody's raising their hand. See? Okay, so that's going to cost you. And that's at every single time step. So, but it does have this amazing stability properties. Okay, so we have 5 schemes now. Right? Euler, forward Euler, backward Euler, leapfrog 2-2, leapfrog 2-4. Lax Windruff right there. Okay? So we got 5 schemes up there on the board so far. Yes? Lang's Windrow is here. Hold on. 30. I don't know. I actually don't remember.
It has an area of stability.
It has an area of stability. Yes.
That's finite. It's not.
Yeah. It's finite. It's actually a pretty good area of stability. You know, my daughter would just make up numbers when she was young. She was just like, "Hey, what time is it?" 45. Okay. She just that's kind of like what I'm feeling like right now. 45. Doesn't even make sense, but you know what? She has an answer, and I have an answer for you too. 45. It's some number. By the way, you know, doing this here, here's my criticism, if I can sort of be critical of what I'm teaching at the moment. So I'm giving you know, you're not supposed to in teaching, like, go teach something and then just go around saying this is all, I don't want to use the words. But here's the thing about this, right? I'm going to show you how we construct stability arguments. This is an important part. But the fact of the matter is this. You can only construct stability arguments such as this and get these numbers out if the equation is super simple. Linear. Linear for sure, and super simple also in the top of it. So, you know, things like ut equals ux, ut equals uxx, ut equals uxxx. I mean, simple things. It's the only things you can do this. Now, if you look at numerical analysis, they spend all this time talking about, oh, look, stability of schemes. All I got to do for you is add a little bit of nonlinearity, non-constant coefficients, and you got nothing. You got nothing. What you know is there's this concept of a CFL. There's just no way you're going to calculate where it is. Okay? So I always tell people, well, look, in practice, if you have an equation, set it up. You know that there's a relationship between time and space. By the way, this is generic for anything that has one time derivative and one space derivative. So you know that, like, you know, if there is a CFL number there, and if I want to double my accuracy, I better cut my time step in half. That's the take-home message for this, is that you have this relationship you sort of have to preserve, even in these other equations, and you can do it. But as far as calculating what the stability boundaries are, this stuff here is kind of rubbish, in my view, because you can't do it for a real problem. You're just going to have to simulate it and see where the thing just blows up on you. Say, oh, probably violated a CFL condition. And then you change your delta t, try to make it smaller, right? That's the simplest thing to do. That always, in other words, one of the things about here, you always notice lambda can only be so big, except for this implicit scheme, where lambda can be anything, but it's always going to be if lambda is below a certain value. Okay? All right, so anyway, just that's a little side note that we have to consider.